Hello and welcome to Real World Machine Learning. Today we are going to be going over data prep, turning 300,000 audio files into training data for a classifier. There's a lot of information here, and so instead of making a long video, we're going to split this up into two different videos. In this first one, we're going to be going over the first two of the 4 Jupyter notebooks, which are Step 0 and Step 1. Before we start this one, go ahead and pause this video and go to the Google Play Store and download Birder.ai. It's the bird sound identifier that can classify over 1,000 different species of birds. It works offline, you can take it anywhere, it's a good app. Go download it. Alright, starting off here with bird selection. The point of this notebook is to whittle down all of the audio files that we have, all the different animals, into just birds and to just 1,000 birds with the most audio data that we can use. We're going to be using Firebase because that's where all of our data is kept at, or all the metadata at least. Firebase is really convenient for us because we had Jupyter, we had Python, and we had JavaScript, and it works in a very similar fashion in both environments. We're setting in birds to 1,000 because we're looking for 1,000 birds here. So first, we went ahead and scraped Wikipedia data for all of these different common names, all the different animals. So we're going to look for all the animals that we have that have the wiki set true property. And of those, we have 4,900. From there, we're going to count which of those are actually birds. And so that's going to be where the sciinfo.class is equal to aves, a bird. And of those, we have 4,400. And now we're going to go ahead and look for a list of the asset counts for each of those classes. So we're going to again find the birds that have the most audio files that we can use for training. And here we're just using again Firebase to loop through all of the animal sounds that we have for that common name and counting them. And then we're going to graph that distribution. So we've sorted and graphed it here, and we can see that we start from about 2,500 assets, and we quickly go down to 1,000 and then below. So we're going to grab the first 1,000 of these classes that have assets. The first 1,000 of these classes with the most assets. And then the main export of this Jupyter notebook is going to be a JSON file called birdinfo.json. This is going to be an array of all of the different classes of birds. It's going to contain all the information that we would need to show in the UI, and it's going to be indexed in the same manner as the classifier. So if the classifier comes up with number 2, then we're going to go looking for index 2 in this JSON file, and that's going to be the bird that was just classified. So with this, we got the bird info list, and then we have our bird names, which is the same common name asset ID counts that we were just graphing before. And we're going to loop through until that bird info list is at least 1,000 long. And for each one, we're going to grab the bird information from Firestore, and then we're going to grab the description and URL that we scraped from Wikipedia, and then we're going to go ahead and base64 encode that image. The URL is just the URL to the Wikipedia page. And then for each one, for each object in that array, it's going to have the name of the bird, the description, the URL, and that actual image. We're base64 encoding that image, that way we don't have to go and download it later on. It's all packaged up in this one JSON file. After those 1,000 birds, we're going to go ahead and append an environmental class. And this is for non-bird audio, so just environmental sounds. So that way, if you're ever running the classifier and it's not a bird that it's detecting, it should be able to pick up that it's an environmental sound instead. And we're going to write all this to that one JSON file, birdinfo.json. Moving on to the next step, this is where we are actually grabbing those audio features out of the audio data. So we have a few steps here. We're going to download all of our audio, and we're going to filter it out so that we will only have pertinent bird audio. And then we're going to save that audio to a CSV file. CSV files might sound a little weird to be saving audio data to, but it's really convenient for the next steps whenever we're going to shuffle this data and grab it back out. So from here, interesting things, we're going to be pulling in pool for multiprocessing, so that way we can do all of this a lot quicker. And we're going to be grabbing Google Cloud Storage because that's where all of our data is stored at. We're setting our sample rate to 16K. If you remember from the intro video, we're using 16K because that's what's really nice and convenient to use on the app side of things. You can interact with the microphone at higher sample rates, but 16K is one that works across the board, and it's also high enough quality that we can train a working model on it. So we landed on 16K, then we have 1,001 classes because we have 1,000 birds plus the one environmental class. We're going to pull in that birdinfo.json file again here, just so that we can reference it, look at the first three and the last three classes for some sanity. Then we're going to build another object of common names and asset IDs. So again, we can see the asset counts that we have per class index. We cap them at 500, so max of 500 audio files per class. And then we graphed it so that way we can see, let's say the first 100 classes have about 500 audio files with them, and then we trail off from there. Except for the last one, which again is the environmental class, and we have a lot more. Okay, so this is the meat of everything as far as the pre-processing goes. This is where we're removing voice audio, we're removing quiet parts, and we're just pulling out the pertinent bird audio. First, we're going to download and convert it to a wave. So if the file does not exist, we're going to download the file. Then we're going to use FFmpeg to create it into a single channel 16K wave audio file. We're using single channel data because that's what's best to pull from the microphone. Some of our audio files are single channel, some are multiple. This brings it all down to one common standard that we can look at across the board. Then we have these three functions: calc freaks, calc amplitude, and calc energy. These are used by the next two functions to calculate the frequency bins within our audio and then how much data energy is within each bin. It's not necessarily the amplitude or how loud each frequency is, more so what is the change of amplitude within that frequency, called the data energy here. Grab these functions from some voice audio detection libraries and had to rewrite them a little bit just so that they worked in the manner that we wanted them to work for bird audio. So the two higher up functions there are connect energy with frequencies, or no, this one, calculate normalized energy and sum energy in a band. Those are what call those few functions above, and they're going to be used by the audio detection function. So here's what's happening. We're going to send in some audio data to audio detection. So here's the audio data. We have a start band and an end band, and audio detection is going to look for how much energy is, how much data energy is in that entire audio sample, then how much data energy is within that band. And if the ratio of the energy in the band is larger than this threshold right here that we set to 0.55, then it's going to say that this is a detected window. If not, it's going to be an undetected window. And at the end of this, it's going to send back two arrays, one array of all the detected audio and one array of the undetected audio. So for example, if we're looking for just voice audio and you have a 30-second recording and somebody's talking for 5 seconds within that recording, after passing that data through audio detection, the first array should be those 5 seconds of somebody talking, and the next array should be the 25 seconds of somebody not talking. This is a little bit more about how it works. We're going to be jumping through that audio sample by in-window samples length, grabbing that little bit of audio. We're going to calculate the normalized energy of that audio. We're going to sum all of the energy within the band, and then we're going to compare right here that the energy within the band to the full amount of energy within that audio. And again, if it's above that threshold that we set to 0.55, then we're going to add it to the detected windows, and if not, it's going to be in an undetected window. And we're going to see here in just a moment while we pass back those two arrays, because we use this function twice, and we use it in two opposite ways. But first, we're going to download all of our audio. And we can see that this is our first parallel task. It takes about 30 minutes to run, and it creates 340 gigabytes of audio data. So we're creating a processing pool of 64 processes, because that's how many cores our box has. For each time, we're going to call the download things function with a common name index, and it's going to sleep for some random amount of 15 seconds. This is so that way all 64 processes don't start at the exact same time. Cuts down on some errors whenever we're downloading things. And then for each asset ID in that common name, we're going to download it, convert it into a wave, and move on to the next one. Alright, and this is where we do the pre-processing, and we're actually filtering all of that audio down into bird audio. So again, we're setting our number of processes up to 64, and our main function here is get features. And here's our pool down here that's going to call that get features function for each of our classes in the number of common names, 1001. And then for each one, alright, so common name comes in, we get the common name from it, or a common name index comes in, we get the common name, the animal name from it. We grab all the asset IDs for that animal. We're setting a max file length of 5 minutes. So for each individual audio file, we're grabbing a max of 5 minutes of that audio. We're opening 2 files, a training file and a test file. Both are CSVs that we're going to be writing to. So when we grab this example out, we're going to be writing it to either a train file or a test file. We're going to be separating that based on the asset ID, as we'll see here in just a moment. Okay, so for each asset, we're going to download and convert it to a wave again. That function will skip if the file already exists, so we're calling it here just to make sure it didn't error out the first time, and if it did, to give it another chance. After that, we're going to read in the data from that file with the sample rate and the audio data, and then assert that the sample rate is the 16K that we're expecting. And here we're creating a key that's either going to be the train or the test, and we're doing this by an 80% split. So 80% of our data is going to be training data, and the other 20% is going to be testing data. That determines which CSV that we write to. As you can see, we're doing this by asset ID. So asset, let's say 2, is either going to be a train or a test audio file. We don't split it later on in the sample section, so that we can make sure all the audio from 2 is either a train or either test. That the model doesn't get to peek ahead for test data because they both came from the same file. And here we're truncating that to our max single file length, and we're doing our first check to make sure that we at least have 8,000 samples left of that audio data, that it's at least half a second long. And here's our first time of calling audio detection. So our first time calling audio detection, we're looking for the range of 85 to 550 hertz. That's our start and end band going in. Then we're passing the audio data, and you can see the 2 arrays that we have coming out. The first array, which is the detected audio, we're trashing. We don't want the voice audio in there. The next array is the undetected audio bits, and that should be everything without the voice, and that's what we want. So we're keeping that. Then we're checking to make sure that we at least have a half second of audio, and then moving on to the next time that we call audio detection. And this time we're looking for the range of 1,000 to 8,000 hertz. And we're doing this and keeping the first array. So we're grabbing any of the audio that detected a high amount of energy within the 1,000 to 8,000 hertz range. This removes any of the quiet parts of the audio, any of the unnecessary background noise. We're left with just pertinent bird audio there, for the most part. Again, we're checking to make sure that it's at least half second long, and then we're writing it to our CSV file. We are converting it to a string in the list and just writing it to file as if it were text. We do this because, like I said, in the next steps when we need to shuffle this data, it's a lot easier to do in this format than if we were to spit it back out as waves and then convert it again. And the last bit of this is we're just graphing to see the file sizes for each of those CSV files to see what it looks like across the board. It's a fairly uniform distribution. Everything has about the same amount of data in it. There are a few, again, the environmental class is a lot more. This class over here has a bit more. But in general, we have a decent amount of training data for every class. So at this point, we have CSV files that have bird audio in them. Next, we're going to actually be shuffling those and converting them into TF records that we can pass into our model. So stick around in the next video for that. But before you do, make sure you go download Birder.ai.